In the last tutorial, I introduced you to the MCS Trace Elements and Isotopes calculator, showed you how to input data for an RFC model, and demonstrated how to use MCS traces. If you have not yet watched that video, please go back and do so before continuing on. Let's navigate to our MCS folder structure, into the MCS VBL code folder, and let's open up the MCS Trace Element and Isotope file. We need to enable macros. And the next pop-up box tells us which version of MCS Traces in Excel we're running, and we can click OK to get rid of that box. And we're going to need to allow Excel to communicate with the MCS folder structure. So just like with MCS phase equilibria, we need to click OK. Make sure that the MCS folder is selected at the top of the window, and click on Choose to get to the main MCS Traces interface. Just like in the last tutorial, the first thing we want to do is select which MCS phase equilibria output file we want to model trace elements and/or isotopes for. Click on the top button to trigger a pop-up window. And using the drop-down menu, we want to select our AFC_tutorial output file and click on Finish. Next, we'll need to pick the trace elements we want to model, so click the periodic table button. And let's hit Load Previous Selection. We're going to model the same trace elements and isotopes that we did in the previous tutorial. Click OK. And to get back to the main page of MCS Traces, we click on Back to Main Menu. In this tutorial, instead of setting the initial concentrations of the trace elements and their partition coefficients by hand, we're going to load them in from a previously created PAR file. This is useful if you have the same Magma and/or Wallrock and/or recharge compositions and other parameters are changing, or if you're using a new composition but you'd like to keep using the same partition coefficients. To load the PAR file, we're going to click on Load or Save Partition Coefficients, Concentrations, and Isotopes from Saved PAR Files. This will make the user form appear where we can upload our PAR file. But before we upload it, I want to bring your attention to these check boxes that are on the left-hand side of this user form. When you are saving to, or in this case, uploading from a PAR file, you can use these checkboxes to select whether you want to load or save partition coefficients, trace elements, or isotopes. So if you'd only like to reuse the partition coefficients from a PAR file, but you don't want to load the prior run's trace element concentrations or isotopic compositions, go ahead and uncheck the boxes. You can also elect to load or save compositions and partition coefficients for the 3 different subsystems, and in the case of the recharge subsystems, up to 5 different recharge events. For this run, we're modeling AFC without any recharge events, so we can uncheck all of the boxes that have to do with the recharge subsystems. Now, I do want to load my isotopes and concentrations, so we'll click those boxes to make sure they're selected. We can select our input file from the drop-down menu, so we want to click on the arrow, and then we'll select this file par_hi_sng_AFC. So if you can't tell from the name, we have a Hawaiian magma and a Sierra Nevada granite Wallrock. And we're going to click on that and click on Load from PAR file. The MCS will upload all of the requested data from the PAR file. So once you click this button, just leave the computer alone until the MCS is finished with this process. If you interrupt loading the PAR file, you'll need to start over again. And once the MCS is finished, we can click OK to get back to the main MCS Traces interface. From here, you're technically good to go and you can finish your MCS Trace Element model, but I like to go through and triple check that everything was loaded correctly. Otherwise, you won't find out that you've wasted your time until it's too late. So we can look at the input sheet for the Magma subsystem by clicking on this button labeled Set Initial Magma Trace Element Concentrations, Initial Isotope Ratios, and Solid Melt Partition Coefficients. If you look at the partition coefficients that have been loaded, there are a couple that stand out just because they're so small. And I've done this intentionally because I wasn't able to find a reasonable, or in some cases, any partition coefficient for that particular element for that particular mineral. And, there's never going to be zero partitioning of the trace element into the mineral, but we don't want to make too many assumptions. So let's set it very, very, very small at 1 times 10 to the negative 6th. And now that we've checked our numbers, it looks like our magma composition and our solid melt partition coefficients are accurate. But remember to click through and double check the solid fluid partition coefficients as well. Let's click on Go to Next to navigate to our solid water partition coefficients. Make sure that they're all set to 10,000. After you have done this, click the Go to Next button again. We need to set these to 10,000 as well, but this time, remember, we have carbon dioxide as the exolved fluid phase instead of water. Once we double check that our compositions and partition coefficients set for the magma subsystem have been loaded correctly, we want to click on Back to Main Menu to return to the main interface. In the last tutorial, we had 2 recharge events triggered, but no assimilation occurred. In this run, we're considering the effects of assimilation, but no recharge events are set. During AFC, the magma chamber simulator allows the Wallrock to partially melt, changing its residual composition as well as the composition of the partial melt. So, in addition to the initial concentrations of trace elements and isotopes in the Wallrock subsystem, we will also need to input partition coefficients appropriate for that Wallrock composition. We're going to do this in the exact same way we did for the magma subsystem by clicking on the next button labeled Set Initial Wallrock Trace Element Concentrations, Initial Isotope Ratios, and Solid Melt Partition Coefficients. Again, our Wallrock is a Sierra Nevada granitoid composition, so the initial composition I've input here looks good. Now I do want to point out that because of the compositional differences between the magma and Wallrock subsystems, the partition coefficients that I've assigned here are different than the ones that have been assigned to the magma subsystem. And that's just something to keep in mind when you're setting your partition coefficients for your own runs. We also need to double check that our solid water and solid carbon dioxide partition coefficients are set to 10,000 because we're not considering the effects of a volatile phase. So click the Go to Next button. Make sure these are all set to 10,000. And click it again to check for carbon dioxide. Once we've double checked that our compositions and partition coefficients set for the Wallrock subsystem have been loaded correctly, we want to click on Back to Main Menu to return to the main interface. From here, we can go ahead and run MCS Trace Elements as normal. Click on the final button, perform MCS Trace Element and Isotopes computation, and come back in a few minutes. Once the calculation is finished, an excruciatingly 3/4 of a girl from Ipanema later, the results are automatically saved as new sheets in your MCS output file, and MCS tells us so by way of this pop-up window. We can click on OK to get back to the main MCS Traces interface again. If you don't have any other trace element models to run, you can go ahead and close out MCS Traces. And remember, do not save the file. This concludes this tutorial on how to run an MCS Trace Elements model using a previously created PAR file. In our final tutorial, I'll walk you how to read this MCS Trace Elements output sheet that gets appended to the phase equilibria output file.